Hello, Geo students. We are on day 8 of our quadrilateral unit, and it's the first day that we are back into proofs. So let's talk about some things that we can say using kind of a proof style format about parallelograms. So when it says, given that we know it's a parallelogram, what can we conclude? All right, well, all those properties that we talked about, you can use them here. So we can say most inherently that the opposite sides are parallel. So we can use parallelogram, and I'm not going to lie, I tend to draw it and put like a little P in there for parallelogram, implies opposite sides parallel. And so over here, let's state the parallel sides. So it should be AB and DC. And then you can also mention that AD is parallel to BC. So we get two pairs of opposite sides parallel. As long as you say opposite sides parallel, you're good to go. All right, for the next thing, we can say that those opposite sides are congruent. And so AB will be congruent to DC, and then same thing with AD and BC, right? But it's not because they're parallel that they're congruent. It's because it's a parallelogram. So that means that the opposite sides have to be congruent. Right? When you think about what else is congruent, well, opposite angles. So angle B would be congruent to angle D, this part here and here. And angle A would be congruent to angle C. So here and here. And our reasoning would be that if I know it's a parallelogram, then there are opposite angles congruent. And now you can abbreviate. You can say like OPP for opposite and, use the angle symbol here. So feel free to abbreviate appropriately, let's say, for that first part. All right, the last piece is that if you have the diagonals drawn in, we also get some extra things that we can say here. The property of diagonals that we know with parallelograms is that they bisect each other. So you have to say that first before you're allowed to say any of the things that come from the bisect. So what I mean by that, we first have to say that AC and DB bisect each other. And if you want to say they bisect each other at E, that's fine too, because that makes sense where they would bisect. But the reason over here is we would say parallelogram implies diagonals bisect each other. So when you think back to like day 4, maybe it was that we talked about all the properties, that was how the property was stated. Now think about when we did triangle proofs. If you were given bisector, you could then say a segment bisector would give you two congruent segments. Well, we really have two segment bisectors. So we're going to get two pairs of congruent segments here. We can say that AE and EC are congruent. And then we could also say that DE and EB are congruent. So if you have both diagonals drawn in, you can get all those little parts congruent. The diagonals are also going to form vertical angles. So anytime you have vertical angles in the picture, you could take advantage of those. So to make life easy, I'm just going to call these 1, 2, 3, and 4. So I could say angle 1 is congruent to angle 2, and angle 3 would be congruent to angle 4. And that's because vertical angles implies congruent angles. And that's not really anything special about the diagonals, just that if you see them in there, you might be able to use that. One other thing that kind of connects from a statement up above. So if I'm going to slide my paper back for a moment. That very first one, the fact that we have parallel lines, I'm going to draw a little arrow all the way down to that number 4 that I just wrote. Parallel lines are going to give us alternate interior angles. And so once you have one of the diagonals drawn in, you could then say that you have alternate interiors. So maybe just for the sake of the argument, if I used, this top line and then I can draw across the diagonal. so that I can get that Z shape, and I'll call this angle 5 and angle 6. You have more than one pair of alternate interiors, but just for the sake of getting it into the notes, I could say angle 5 is congruent to angle 6, and that would be parallel lines implies congruent alternate interior angles. So there are some new reasons we're allowed to use, but then there's also the old reasons that we had from before that we can connect with those. All right, let's move right on over to the next page. Page 32, we get a chance to put them to use here. So what we are proving in most cases are congruent triangles. So as a little review, ways to prove congruent triangles. Think of the 5 methods that you know. Side, 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 angle, side, angle, side, angle, 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 side. And then there's that special case of ASS, which we refer to as HL. So if you have right angles, maybe you're able to use that. All right, this very first one, you're asked to prove that triangle ABD is congruent to triangle CDB. So it's only 2 triangles there. But the only given that you have is that you have a parallelogram. So any of those details that we know about a parallelogram, we can use here, which means there's actually multiple ways to do this proof. And now parallelogram, you can write the whole word out. You can draw the little parallelogram with the P in it. I know other teachers call it like P-gram to try to abbreviate the notation here. Any of those are perfectly fine. All right, so think about all the properties. I'm going to bring back that last page for a second here. So we could use parallel lines. We can use opposite angles and sides being congruent. We have a diagonal, so we could get alternate interiors. There's so many things we could do here, right? So if we start with just maybe some opposite sides congruent, we have AB and DC congruent. That'll get you a pair of sides right there. And then we could use the other pair of sides. AD and BC. And so here we would say parallelogram implies opposite sides congruent. Sorry if you can hear, that's Teddy in the background. Our little golden doodle, probably barking at the mailman or something. All right. For the next thing, we could get some angles, but don't forget, we had a little reminder about vertical angles, but you can also use reflexive. So if they share that side BD right down the middle, heck yeah, use it. So BD is congruent to itself by the reflexive property, which gets us a third pair of sides. And I would probably say that's like the fastest way that we could prove these 2 triangles congruent. So we can go right to saying triangle ABD is congruent to triangle CDB by side, side, side. And now to be honest with you, you could use any method other than HL to prove these. We could have gotten any number of angles from the opposite angles here to the alternate interior angles. So we could have used any method other than HL to do this. So keep that in mind, that there is a lot of flexibility, and you might see one thing and I might see something else, and that's okay. Right? For number 2, you got ABCD, this little piece is a parallelogram, and then they hand us a pair of angles, and we're trying to prove, that DBE is isosceles. I'm just going to highlight that so I can focus on it in the picture. So DBE, DBE, all right. So back in our congruent triangles unit, we talked about to prove isosceles, that was usually steps beyond CPCTC, meaning we still might want to get triangles congruent and then go past that. So something to think about. We may or may not need that depending on what's being given, but just food for thought. So let's see what the givens provide us with, and then we'll go from there. So we have ABCD is a parallelogram. And to be honest with you, since there's so much stuff that could be said here, I'm actually going to put the next given in there with it, just to kind of see which direction it is pushing us. So angle ABD ABD, that's this guy, is congruent to angle E. That's that guy down there. All right, that's also given. The reason I wanted to kind of look ahead is just because isosceles can be achieved by saying you have two congruent sides or you have two congruent angles. The fact that they're handing us angles here makes me think that our goal should be to prove the congruent base angles to get the isosceles, all right? And if you look at the picture, angle E would be one of the base angles already. So if we can somehow get it congruent to the other base angle over here, that might be the way to do it, right? Well, what the heck does that have to do with the angle ABD? Well, that's at least inside the parallelogram. And if we look, I can kind of see that Z shape showing itself right there. That's part of a pair of alternate interior angles. So if I want to talk about alternate interior angles, we first have to talk about parallel lines. So let's use that parallelogram to give us parallel lines. So specifically, the ones that I traced out would be AB and DC. But if you're ever not sure, then just state both pairs. So opposite sides parallel. If you want to in that same step, feel free, cover your bases. You could say AD is parallel to BC, and then you'd never have to worry about, did you say the right pair or not? From here, let's look at those angles. We've got angle ABD then would be congruent to this angle down here, BDC. And that would be because parallel lines gives us congruent alternate interior angles. Ooh, all right. We've got this angle congruent to this one, which is the other base angle here. And we know that those two are congruent. If we go way back to the start of when we learned proofs, there was a rule that said if A is equal to B and B is equal to C, then A is the same as C, right? Kind of like cutting out the middleman. Well, if we know that angle E is equal to ABD and BDC is equal to ABD, we should be able to say that those two are equal, which was kind of our goal here, to get the base angles congruent. That property is called the transitive property, excuse me. Right? And so that was connecting, step 1 and step 3. You don't have to say that, but in case you're like, where the heck did I, use transitive? It was between here and here. Oh, here, excuse me. All right, well, now that we have this angle congruent to that angle, those are congruent base angles, and we can say that triangle DBE is isosceles because two congruent base angles means I have to have an isosceles triangle. Ooh, that's a proof we haven't seen in a little while. The idea of using, transitive property to get to our final steps. All right, let's see if we can do one more together in these notes. So for number 3, they're giving you a parallelogram. You've got both the diagonals. What you're being asked to prove here is that triangle AED. So I'm going to just highlight that. That's this guy. Triangle AED is congruent to triangle CEB. CEB is this guy. I feel like this is a proof that you could probably tackle on your own. If you're feeling comfortable and you're like, I think I got this, give it a try. We'll talk about it in class. And know that there's many ways to solve this. So you could use a lot of different methods to get there. The one I wanted to look at together is number 4. So down at the bottom, you're given that ACFD. So the whole big figure here is a parallelogram. And they hand us a pair of congruent angles, angles 1 and 2. And then you're going to try to prove, I grab my colors again, that ADE, this triangle right here, is then congruent to triangle CFB. So CFB. So anytime there's more than two triangles, it's a good idea to just make sure you know like what you're looking at. So if you have a couple colored pencils sitting around, it's always helpful here. All right, so let's take a look. Parallelogram is the new step. So we want to think about how that can get us some congruent parts of those triangles. So ACFD is a parallelogram given. If you'd like to put angle 1 and 2 are congruent right in there, go for it. That's perfectly fine, right? So that's going to hand us a pair of angles right off the bat. So that's kind of nice. All right, now think parallelogram. We know opposite sides parallel. That's not going to be super useful here, but opposite sides are congruent. And if I look, AD and CF, those are opposite sides in that big parallelogram here. So we could use that. AD is congruent to CF. So parallelogram gives us opposite sides congruent. So there's a pair of sides, right? And then run the gamut. What else? Opposite angles congruent. If you look, because there's a lot going on in the middle, it's almost a touch distracting. But if I look at the big picture, angle D here and angle C up here, those are opposite angles in that big parallelogram. So I can make step 3 that angle D and angle C are congruent. And my reason would be parallelogram implies opposite angles congruent. And then there's 3 pieces of it. I got 2 angles and a side. All I have to look at is what configuration they're in the diagram itself. So remember, you cover up so that you're focused on just one triangle. I have 2 angles and I have the side connecting between them. So that's a perfect example of angle, side, angle to be able to prove that triangle ADE is congruent to triangle CFB, and then by angle, side, angle. Done. All right, guys. Make sure to go answer that post video question, and I will see you soon.